We've looked at the basic pattern for integration by substitution. Again, we want to stress the idea that what we're looking for is a composite function, and we're looking for that interior function to make our substitution. So let's go ahead and start working some simple substitution problems from beginning to end, showing these steps. Now, when I say simple substitution, I don't mean that these problems are going to be easy. Usually integration by substitution takes a little while to catch on to. It can be a tough concept. What I mean by simple substitution is we're going to get substitutions that swap out nicely for everything in our problem, versus some later examples will be a little bit trickier to come up with. So what we're looking for in each example is, again, that interior function. So in this case, we want to let u equal 7x plus 7. Then what we want to do is consider the derivative of that statement. So du over dx should equal the derivative of 7x plus 7, which in this case is going to be 7. Multiplying the dx over to the other side will give us du equals 7 dx. So what we have, that 7 dx, matches up exactly with the rest of the statement in our integral. So in place of 7 dx, we can substitute in du, since we have this identity. This means we can rewrite this integral as u squared du. So if we work the steps of our substitution correctly, we should end up with a problem that's going to be simpler to evaluate, something that matches up with one of our basic derivative properties. So the integral of u squared is going to become u cubed over 3 plus some constant c. Then our last step is to turn this back into, rewrite this back in terms of the original variable. So in place of u, we'll plug this 7x plus 7 back in. So we'll undo that substitution we made at the beginning. This will become 7x plus 7, that quantity cubed, divided by 3 plus some constant c. We'll start off the second example the same way. We want to identify the interior function, which in this case is 5x. So we're going to let u equal 5x. We'll again look at taking the derivative of u, which should be equal to the derivative of 5x, which would be 5. Getting du isolated on one side by itself gives us du equals 5 dx, which again we have exactly 5 dx as the rest of that integral expression. So in place of that 5 dx, we're going to be able to swap in du. So we can rewrite our integral as the integral of e to the u du. And again, we've got now we have an indefinite integral that is identical to one of our basic integration properties. So this is going to become e to the u plus c, and then replacing u with what we originally swapped out. This will become e to the 5x plus some quantity c. In example 3, we have something of the form 1 over x here. So our interior function is going to be 2 plus 5x squared. So we'll let that swap in for u. So taking the derivative of u should be equal to the derivative of 2 plus 5x squared, which should be 10x. So we get du equals 10x dx. So what we're looking for once we get this du isolated by itself is to find this expression somewhere in that integral so that we can swap that out and now have this du expression. Since our independent variable is now u, we want to integrate with respect to u. So we need that du statement in there to complete the integral. So this will become the integral of 1 over u du, which integrates as the natural log of the absolute value of u plus some constant c. And then swapping back in our original expression for u, we get the natural log of the absolute value of 2 plus 5x squared plus that constant c. In example 4, again, we identify that interior function, in this case 2x minus 5. du over dx is going to equal, in this case, just 2, the derivative of 2x minus 5. So we get du equals 2 dx. So again, what we're going to look for is to find that 2 dx, this expression, in that original integral. In this case, we have it, even though it's split up. So we can replace the 2 and the dx with this expression du, so that now we'll have the integral of u to the negative second du. So integrating will give us u to the negative 3 over negative 3 plus some, we want to make sure we're adding 1 to that, so adding 1 would make that u to the negative 1 over negative 1 plus some constant c. We can rework this a little bit. We can bring that negative out in front of the fraction. We can write u to the negative first as a u in the denominator. So this will become negative 1 over u plus some constant c. And then swapping back in our original expression for u, we get negative 1 over 2x minus 5 plus some constant c. Our last example for these simpler substitution problems, we've got our interior function 1 minus 6t. So finding that derivative and then solving for du will give us negative 6 dt. So that should just be the derivative of 1 minus 6t. So what we have to swap out is negative 6 dt. We have the dt, and we have a negative 6. So for those two pieces, we'll be able to swap in du, which will give us the integral of e to the u du. So the integral of e to the u is just e to the u plus some constant c. And then we'll swap back in that original expression for u, which is the 1 minus 6t, to get our the final result for that indefinite integral.